Hello, welcome back to A Slice of Physics. Having discussed the concept of charges and their interactions, we're now ready to get into Coulomb's law, which defines the force between two charges. As we discussed in the previous video, the direction is given by the fact that like charges repel each other and unlike charges attract each other. And Coulomb's law also gives us the magnitude of the force between these charges, which is what we're going to discuss now. We know that charges apply forces on each other. So if I have a charge here that's Q1 and another charge here that's Q2, they will apply a force on each other. And whether that force is attractive or repulsive depends on the type of the charges. If both of these are positive, the forces will be repulsive. So the force on each charge will point directly away from the other charge. Same thing if both are negative, the forces are again repulsive, so it'll point away from the other charge. And if one of these is positive and the other one is negative, the forces would be attractive, so the force on each charge would point toward the other charge. So that gives us the direction of the force. The magnitude of the force is given by Coulomb's law, which states that the force of charge 1 on charge 2 for magnitude equals the force of charge 2 on charge 1, and that's given by K times the absolute value of Q1 times the absolute value of Q2 divided by square of the distance between them, where r is the distance. So in this case, r here is the distance between the two charges. So let's look at this equation a little bit and understand the different pieces of it. First, it's telling us that the force of 1 on 2 equals the force of 2 on 1 in magnitude. In fact, these are Newton's third law pair of forces, so they will always be equal in magnitude and opposite in direction. Now that might be counterintuitive. So if you have a 1 Coulomb charge over here and a 10 Coulomb charge over here, you might expect the 10 Coulomb charge to have a larger force on the 1 Coulomb charge than the 1 Coulomb charge's force on the 10 Coulomb charge. But that's not the case. And by the way, this equation is similar to an equation you saw in Physics 1, which was the force of gravity given as the gravitational constant times the mass of one object times the mass of the second object divided by the square of the distance between them. And this was also the force of mass 1 on mass 2 as well as the force of mass 2 on mass 1. If you remember, the gravitational force that the Earth applies on you is equal to the force you apply on the Earth. Now your acceleration because of that is a lot bigger than the Earth's acceleration because of the difference in masses, but the forces are equal in magnitude and opposite in direction in that case as well. So it's good to see these patterns and analogies in physics to get comfortable with the various concepts. And while we're comparing these two forces, force between charges and force between masses, it's also good to note that while the force between charges can be attractive or repulsive as we saw, the force between any two masses is always attractive. That's one difference between the two. So this G here was Newton's gravitational constant, and similarly for the electrostatic case, this K is called the electrostatic constant, and it equals 9.0 times 10 to the 9 Newton meter squared per Coulomb squared. Second, we take the absolute value of these charges Q1 and Q2. We don't care if they're positive or negative, we just take the number part of it. So the sign of the charges is irrelevant to the magnitude of the force between them. And all of that is divided by the square of the distance. R in this equation and in a lot of physics equations is the distance, not necessarily the radius. So this is the distance between the two charges. And you can see that if I take just the units, K is in Newton meter squared per Coulomb squared. If I multiply that by the absolute value of charge Q1, that'll be in Coulomb. And again, absolute value of charge Q2 also in Coulomb, and divide all of that by square of the distance in meters, so that would be square meters. This c times c is c squared, and that'll cancel the c squared over here. This meter squared at the bottom will cancel the meter squared over at the top, and so I'll end up with a unit of Newton, which is the SI unit of force, so all of that works out well. So let's take an example of two specific charges at a given separation from each other and see what the force in that situation would be. Let's say I've got a plus 20 nanocoulomb charge sitting over here, and there's another charge to its right that's plus 50 nanocoulomb charge. And let's say the distance between them is 5 centimeters. So in this situation, we want to know the force of one charge on the other and the other charge on the first. So let's call this Q1 and Q2 over here. So F of 1 on 2 would be K times Q1 absolute value times Q2 absolute value divided by square of the distance between them. And now if I substitute the numbers in, this would be 9.0 times 10 to the 9 Newton meter squared per coulomb square. I'm not going to write the units, times 20 nanocoulombs. So I'm going to write that as 20 times 10 to the negative 9 coulombs. It's important to convert that to coulombs from nanocoulombs because the constant is given in terms of coulombs. And so if I simply write 20 nanocoulombs, then it won't cancel this coulomb over here. So that's why I got to make this conversion. And then for charge 2, I take 50 times 10 to the negative 9 coulomb again. And I've left the sign out. Even if these were negative charges, the sign will not play a role here because I only want the absolute values of the charges. And then I divide by square of the distance. The distance is given as 5 centimeters. And I want to convert that to meters because, again, the electrostatic constant is given in terms of meters. So this would become 0.05. Some of you might write this as 5 times 10 to the negative 2. That's fine as well. So you go from centimeters to meters, and then you square it. And the rest of the work can be done by a calculator, and this will give you 3.6 times 10 to the negative 3 Newton. So that's the magnitude of the force of 1 on 2. Where would you show that force? This is the force of 1 on 2, so the force must begin at charge 2. And that's its magnitude, 3.6 times 10 to the negative 3 Newton. What would its direction be? These two charges are positive, so they will repel each other. So charge 1 will repel charge 2, so the force should be shown like this. This is F1 on 2. Now in terms of magnitude, Coulomb's law tells us that this is also equal to F2 on 1. How would I show that in the diagram? Well, force of 2 on 1 is applied on 1, which means I got to show the force beginning at charge 1, and the force on charge 1 will be away from charge 2. Charge 2 is also going to repel charge 1 because they are both positive, so this force would act in this direction. Same length because the magnitudes are the same, so this would be F2 on 1. Some of this is hopefully a review from Physics 1 on how to show force vectors acting on different objects. The only new concept here is how you got the magnitude of the force. It's now based on the charges and the distance between them and this electrostatic constant. So now you see that these two forces are equal in magnitude and opposite in direction. That will always be the case. So if I had two negative charges, the forces they apply on each other will also be repulsive and equal in magnitude. So once again, you see that they are equal in magnitude and opposite in direction. And if I had a positive charge over here and a negative charge over here, those forces would be attractive. So once again, equal in magnitude and opposite in direction. These two forces will always follow that pattern because they are Newton's third law pair of forces. Every action has an equal and opposite reaction. This slice of physics covered Coulomb's law, where we understood everything about the force between two charges. We had already seen that their directions are dependent on their specific types, positives and negatives. We get that using this fact that opposite charges attract while like charges repel. And the equation form of Coulomb's law gives us the magnitude of the forces, which depends on the absolute values of the two charges, the distance between them, and this universal constant called the electrostatic constant. And we saw that the forces of the charges on each other form this Newton's third law pair of forces. So they're always equal in magnitude and opposite in direction. Thanks.